right. Here a solar cell has a thin coating of thickness d to reduce the reflection of light. White light incident on the coating is reflected from the top and bottom surfaces of the coating. Right here, this is important. What, right? White light incident on coating is reflected from top and bottom surfaces of the coating, right? Reflected from top and bottom, right? Reflected from top and bottom surface of the coating, right? This produces a final reflected beam as shown here. Is a final reflected beam, and here's the incident white light. Okay, explain why some wavelengths of incident white light will be missing from the final reflected beam. Here light has reflected, okay, right. Then how is it possible? uh, the point here is you should know, right, the reflected one. Here we have two beams, right? For reflected one we have two beams, right? So here this is the one reflected from top surface, this is the one reflected from bottom surface. So when they superpose, right, when they superpose, what happen? Constructive interference occur and destructive interference occur. Here they ask, explain why some wavelengths of the incident white light, some wavelength, right, will be missing. The reason is they are destructively interfere with the other beam, right? So we are going to write this one, right? First thing, one, due to interference, right? Oh, you can make it like this, right? Interference occur, right? Interference occurs between two, oh damn it, it's not, between two reflected beams. Next point, what, destructive interference occurs destructive interference occurs when two reflective waves when two reflective waves meet in antiphase. Meet in antiphase. Right. Then what happened, right? If the path difference is equal to, if the path difference is equal to what, n plus half times lambda over 2, right? This one, right? And here you should know, right, for destructive interference we have two conditions, right? One is if they are antiphase, right, we can tell the conditions for destructive interference in terms of phase. If they are antiphase, right, definitely they will destructively interfere, right? Or if their path difference is, right, n plus half over 2 times lambda, then definitely they will destructively interfere. So these two are the conditions. So you should mention that probably they're gonna interfere, right? 1 mark for this one, right? 1 mark for this one, right? And they should destructively interfere, right? They should destructively interfere, you should mention that one. and you should mention what are the conditions for destructive interference, right? Okay. So if you have these 3 points, you will get 3 marks, one for this point and one for this point and one for this one, right? Here, white light is incident perpendicular to the surface of the coating. Calculate the wavelength that would be missing from the final reflected beam. Assume the refractive index is 2.3 for all visible wavelengths, right? So how can we calculate this one, right? As I told you, right, the path difference we can write as d equals what, n plus half, right, times lambda over 2, right? This is the condition, right? This is the condition for destructive interfere in terms of path difference. So if I take 2d, that is equal to n plus half times lambda, right? So what they are asking from us is to calculate the wavelength that would be missing from the final reflected beam, right? Final reflected beam. Okay. Then how can we find that one? First thing, we can calculate the path difference, right? Path difference. So path difference is equal to 2 times d. I'm taking 2d because I take this 2 to here, or either you can take directly d and substitute other values for here, then you will get the same mass. It's okay. So I'm going to calculate 2d. So it is 6.5 times 10 to the power minus 8 meters times 2, right? Then it will give you what, 1.3 times 10 to the power minus 7 meters, right? Then what I'm going to do here, I need to calculate wavelength of the coating, right? Wavelength of the coating, which means this lambda. But you should know the minimum occurs when n equals to 0, right? When n equals to 0, right? That is where minimum occurs. So you can take what, then path difference or 2d is equal to what, here if n is 0, then it is lambda over, we call lambda over 2, right? Then to take lambda, or what we call wavelength in coating, right? Wavelength in coating. So that is equal to what we call lambda. It is equal to 2 times 2d. We have already calculated 2d over here, so I'm going to put that one, 1.3 times 10 to the power minus 7 meters, right? So we can calculate the wavelength in coating, right? In coating, right? So it is 2.6 times 10 to the power minus 7 meters. So by using this equation, we calculated what, wavelength in coating. But here they are asking what, wavelength that would be missing from the final reflected beam, right? Final reflected beam. But we have calculated wavelength in coating, right, by using this equation for this the condition for destructive interference, right? How can we calculate that one? I think here they have given us refractive index. Why they have given us refractive index? That is the point right here, right? We all know the refractive index, refractive index is equal to speed of light in vacuum, speed of light in that particular medium, and we all know c is equal to, we can write f lambda, right? Here lambda is in vacuum, or we can tell it in air, right? Then here we can write what, f times the same frequency, we have no difference in frequency, times lambda times what, coating, right? In that medium is coating, right? So if you wrote it like this, n equals f times lambda a in air over f times lambda c, because our c equals this one and v equals this one, right? Then f will be cancelled out. Then we can write, we want to find out lambda a because we know lambda c, this is lambda c, right? Then lambda a, which we call uh, wavelength in air, right here, wavelength that would be missing from final reflected beam, right? So wavelength in air is equal to n times wavelength in that particular medium we call coating. In our scenario it is coating, so it is n times, n means 2.3, sorry, 2.3 times 2.6 times 10 to the power minus 7 meters, right? So if you calculate this one, you will get what your answer as 598 nanometers, right? 598 nanometers. And you have to put your simplified answer over here. It is 5.98 times 5.98 times 10 to the power minus 7, right, meters. So you can write it as 598 nanometers, but our answer should be in correct significant figures, or in the form of what they have given their data over here. It is the, here they have given their data in this scientific notation, so we have to put our answer in that notation. So it is so if you make it into correct significant figures, it is 6.0 times 10 to the power minus 7 meters, right? I hope you understand how we got this answer. We applied destructive interference to our here. Then we can take d equals n plus half over 2 equals lambda. That is the condition for destructive interference, and because of this coating, light beam is destructively interfere. So we can get lambda, which means wavelength in the coating, by using this equation. So we took it, and by using the definition of refractive index, we took, right, what we find wavelength in air, which we call wavelength that would be missing from the final reflected beam, right? Here a solar cell array is placed on the roof of a house as shown. The area of the solar cell array is 8.7 square meters. The roof of the house slopes at an angle of 60 to the horizontal, shown below. When the intensity of radiation from the sun perpendicular to the surface of earth 1.1 kilowatt per square meter, the output of solar cell array is 5.7 10 to the power 6 joules per hour. So what they have mentioned over here, right here, right, look at here, right, when the intensity of radiation from the sun perpendicular to the surface of earth is, right, you should know that one, right? Here they have given, if this is our earth, this is the direction of the intensity, so it is 1.1 time 1.1 kilowatt per square meter. So here also we will face the same situation, and you should know what the angle between which we call intensity and this roof. So what is it, right? From geometry, right, here, right, if I draw an angle, right, like this, what will happen? Here it is 90, and here it is 30, and here also we will get 30. So we have 30 over here, right? Then here they have given the output solar cell array is 5.4 times 10 to the power 6 per hour. And you should know what here, right, they have given watts per square meters. Here it is about what joules per hour, right? So we have to deal with one kind of unit. So I'm going to convert this one into watts, which means into the power, because in terms of power we can find the efficiency. What is efficiency? Efficiency is equal to useful power output over power input. Okay, first of all that, right, let's calculate, right, for input 1, right, useful input power input is equal to 1.1 times kilowatt. So I'm going to make it into the power 3 watts, right, watts, times here, right, we need to make it into the perpendicular direction, right. Then 1.5 times, here it is what, sine 30, right. Keep in your mind what here, when we are taking intensity, that we call intensity is what you call intensity is power per unit area, but that area should be perpendicular to that power, right, or it's like pressure, right, when you write pressure, it is F over A, but we all know that force should be one perpendicular to this area when you're taking pressure. Like the same principle we used here, that our power source coming from the sun is not perpendicular to the surface over here, then we need to take the component, its component perpendicular to this one. So it is sine 30, right, sine 30 sine 30 times, and here it is per square meter, so we have 8.7 square meters, right. Here we have 8.7, so right, we need to multiply it from 8.7 square meters. Then we will get here it is m minus 2, then m minus 2 will cancel out, then we will get our answer in watts, right. So it is 4.785 times 10 to the power 3 watts, right. Then I'm going to calculate power output, or we call it useful power output, right, useful power output, right, useful power output, right, that is equal to, here they have given this 5.4 times 10 to the power 6 joules per hour. So we all know the power is energy per unit time, so it is energy over t, which you call time, right. So here it is 5.4 times 10 to the power 6 joules over 3600 seconds, right, it is 60 times 60 seconds, so you will get 1.5 times 10 to the power 3 watt. Now you can calculate the efficiency, right. So efficiency is equal to useful power output useful power output over in power input, right. Here it is useful power output is 1.5 times 10 to the power 3 watt, and here it is 4.785 times 10 to the power 3 watt. So if you simplify this one, you will get 0.313, or we can keep our answer over here, it is 0.31 if you make it into correct significant figures, right. Here I have to explain the way that they have given marks for these questions, right. Here for the final answer you will get 1 mark, and by using this concept, what we call useful power output over power input, 1 mark for this one. And here we have taken it by converting it, we have converted it into watts by taking the power, so they have given 1 mark for this one, and for here they have given 1 mark, so it is 4 marks for this one. And here, right, here for finding this one, 1 mark, and for this one 1 mark, and to take this one mark and here 1 mark, right? Right, if it is not a show that question, if it is not a show that question, if it is about calculation or other things, if it is not show that question, if your final answer is correct, you will get full marks, right? You can use any other method of steps, right?